Right. Welcome to the first talk of the second week. The talk will be given by Jeremie Beck, who is well known to everyone in Bangalore and ICTS. He is at the CNRS at Indria, Université Côte d'Azur. Today he will be talking about anomalous dissipation and spontaneous stochasticity in deterministic surface quasi-geostrophic flow. I should say that the three talks today in the morning session are all 40 minutes each because the speakers requested 40-minute talks, but they're around and there's lots of time for discussion. Thank you very much. Jeremie?
Yes, thank you, Rahul. So first, I wish to thank you, Rahul, Uriel, and Kostya for setting up this program and for giving me the chance to give a talk on recent things. So I'm going to talk about some general consideration for the limit of inviscid inviscid flow in the context of turbulence, and in particular in the context of quasi-geostrophic flows. So hoping that I'll be able to introduce the problem, to tell you what is a quasi-geostrophic flow, and to show you the results. And basically, this is mainly the work that Nicolas, who is here, has started for his PhD. So don't hesitate to ask us questions. And it's a common work also with Simon Talabar from the physics department in Nice. So basically, the motivation is to try to understand the limit of vanishing viscosity of statistically stationary solutions to the Navier-Stokes equation. And with the question of being able to assess or not whether one can neglect the viscosity and think in terms of inviscid Euler dynamics at very, very large Reynolds number or very, very small viscosities. And so what is known from observations of turbulent flow is that this inviscid dynamics is giving some answers to the turbulence problem. So in particular, if we look precisely to the scale-by-scale budget in a turbulent flow, we know that the contribution from viscosity is almost absent in the inertial range, except that it's giving some dissipation. And this dissipation, which can be seen as a transfer. So the second thing is that there has been some numerical experiments in the group of Marchetti and Brachet, who showed that if you take the Galerkin truncated equation, Euler equation, inviscid Euler equation, then you have a transient regime before thermalization, where the inviscid dynamics is giving a turbulent-like statistics, like K-isothermal spectrum and other things which are very related to what is observed for finite but large Reynolds number. So now, the question is to understand to what extent do the Euler equations are describing turbulent flow, and in particular, if there are important symmetries which are broken in the limit when we take viscosity to 0. So one of the first essential symmetry which is broken in a turbulent flow is time reversal, which is a consequence of the fact that there is a dissipative anomaly, so that if one is looking at the kinetic energy dissipation, this kinetic energy dissipation has a finite limit in the limit of vanishing viscosity. So the energy dissipation is written this way. So the brackets can be either some ensemble average or some spatial average. So that's not very, very important at that level. And so basically, these are typical measurements in different numerical simulations, I mean, for the last 30 years, showing the rescaled dissipation, so in non-dimensional units of your system as a function of the Reynolds number. And what you see is that apparently when you take Reynolds larger and larger, what you get is a finite plateau, which means that there is a finite limit for this kinetic energy dissipation, which means that somehow this is breaking one of the symmetries of Euler equation, which is the conservation of kinetic energy, which relates to the time reversal symmetry. Okay, so this is one of the breakdown which is essential in order to tackle this inviscid limit. So of course there is there are some understanding and some theories about this dissipative anomaly, which dates back from Komarov, from 1940, from the 40s, through what is the celebrated four-fifth law, so which is telling you that the dissipation somehow relates to the skewness, to the asymmetry of the moments, of the increments of velocity, and basically, so this thing is going together with a conjecture of Onsagar, so which is now a theorem, which is stating that in order to get a finite dissipation in the inviscid limit with zero viscosity, one has to observe that velocity increments are scaling like a power of the separation over which they are computed, and the exponent has to be less or equal to 1/3. So this has been recently proven for weak solutions to the Euler equation. And recently, I mean, less than 10 years ago. And so basically, this means there are two things. So this means that in the limit of infinite Reynolds number or vanishing viscosity, turbulent velocity fields are rough, they are non-differentiable. And then the idea is to try to construct dissipative weak solution to the Euler equation. So weak in the sense that it's not something where you have to think about the equations in terms of testing it against test functions, and you don't apply directly the derivative to the solution. Or in other words, it means that the velocity field is not a function, is not a differentiable function, but rather a measure as a function of space. But then there has been for the last 15 years or so, many results, even more than 15 years, many results showing that at the end, almost all non-smooth initial conditions, which are satisfying this Onsagar criterion, are non-unique in the sense that, so there are different results. And in particular, there are some results saying that the set of solutions, of initial conditions for which the solution is non-unique is dense in appropriate spaces of initial conditions. So basically, this suggests that certainly just the dissipation of kinetic energy is not enough as a criterion. And so we need to maybe think about other broken symmetries. So there is another thing which is well known also for some time. So since the work of Obuchov and Komarov in the 60s, is that actually there is another broken symmetry of the Euler inviscid dynamics, which is scale invariance, which is not satisfied in the limit of vanishing viscosity. So solutions to Euler equations are unchanged if you do this kind of scale transformation. But what we know from numerical measurements or experimental measurements is that actually if you look at the structure functions of the velocity field, again, so now you look at p order structure functions, what they display is some anomalous scaling, so which means that somehow the exponent of the scaling law of this increment to the power p is not just a linear function of p. And so this is well documented, and this is universal, in the sense that all these exponents seems to be the same independent of the kind of flow you're considering. In other terms, it means that, so if you think in terms of probability distribution of this increment of velocity, so basically at varying scale and rescaling it by its standard deviation, what you observe is that it's not self-similar in the sense that the distribution is displaying fatter and fatter tails when you decrease scale. And this is these two things are equivalent. So now, so this is another broken symmetry, and there are other things which are coming into the game, which are related to a breakdown of various flows. So the first flow which is breaking down is the Lagrangian flow. So this is known since the work of Richardson. So now this is almost a century ago that Richardson proposed this scaling. So basically, if now you consider fluid particles, so which are just characteristics of the velocity field, and you are interested in the relative dispersion between two solutions to these equations and look at the distance between them, basically, you can, just by dimensional argument, say that the time derivative of this distance will be some power h of the distance itself, with this h less than 1, of the order of 1/3, if one is believing in the Congress of 1941, and which means that these solutions to this kind of equations are non-unique. Okay, so you cannot define in a unique manner. So if you look at this equation here, so this h being less than 1, it means that the right-hand side is not Lipschitz, so which is the thing that we need to prove the unicity. And in particular, you can see that for this specific case, you can have two solutions, one which is r equal to, and if you start at r equal to 0, you can have two solutions, one which is r is staying equal to 0, and another one which is r is going to some t to some power, where the power relates to the exponent h. So now, basically in turbulent flow, if you look at such separations inside the inertial range, of course, what you can see is that the mean square distance between tracer particles is attaining a regime which is where it's growing like t cube. So this is the celebrated Richardson law, and both. I mean, and this if you condition to some initial or final separation. So which means that either if you go forward or backward in time. And typically, so these are results from numerical simulations, which are showing curves correspond the square separation, the mean square separation corresponding to various values of the initial distance between tracer particles. And what you see is that after some transients, which correspond to first ballistic motion, the ballistic separation between the particles, everything is going to a universal law, which is becoming independent of the initial separation. So which means that now, if you take the limit when you make viscosity to 0 and this initial separation to 0 also, what you will observe is something which will collapse to this T cube, both backward and forward in time, and which will become explosive in the sense that two particles with an initial separation which is 0 could separate in to a finite distance in a finite time. And this is much more, a much stronger separation than in a chaotic system, for instance, where in a chaotic system, the separation is growing like initial separation times some exponential in time. And when you make the initial separation to 0 in a chaotic system, you recover 0 for the separation. Here, it's not the case. You can think about that as if you are considering two diffusing particles with independent realization of the Brownian noise, so that which are starting from the same point. So as they are following independent realization, I mean, they just separate in an independent manner. So then there is another breakdown of a flow, which is this time Eulerian spontaneous stochasticity, and this which relates to some. So this was touched upon by Nigel last week. So it was introduced. I mean, the concept was introduced by Lorentz. So it's not. It has nothing to do with what is now called the butterfly effect, because it's a very strong butterfly effect, if you want. And basically, it's leading to very drastic unpredictability. So the idea is the following: is to say that now if you take a solution to a system which is nonlinear at all scales, if you want, basically, as soon as you perturb it, you have a growth of the perturbation which is nonlinear itself. Okay, so the way Lorentz is formulating it consists in saying that he's considering fluids which are having a sufficient amount of kinetic energy at small scales. And so now this has been a bit put back to today's language somehow, essentially by two persons. I mean, Palmer, who is a meteorologist, who is investigating predictability in various meteorological flow, and Alexei Mailyabayev, who is more from the mathematical physics community, and who is investigating this problem of Eulerian spontaneous stochasticity in different settings. In particular, so this work in 2016 is a first work he did on this aspect, on the considering shell models of turbulence. So now, together with Alexei and Simon, so what we have treated an example, which is the two-dimensional Kelvin-Helmholtz stability, so the vortex sheet. So I mean, I guess everybody is knowing it. So you start from a vorticity distribution in 2D, which is distributed on the line, which means that you have a discontinuity, a shear discontinuity of the velocity with a velocity to the right and a velocity to the left plus u minus u above and below this line. And this is a well-known instance of hydrodynamical instability. And so now, basically, what you do is that you start from this singular velocity field. You put different regularizations. So, for instance, you put a viscosity to the flow, and you put a small noise to perturb this interface, which with an amplitude epsilon. And the thing is that when you make both the noise and the regularization to 0 simultaneously, or at least so the thing which is important is that the viscosity is going to 0 first. What you get is that the mixing layer is developing and is reaching a finite size in a finite time, independently of the fact that you have prescribed this limit. And so you can see it from this picture, which is showing the separation energy. So basically the integral of the square of the difference between two solutions, which are starting with two different noises, as a function of time. And so what you see, and for different values of the viscosity, of the regularization, and at the same time, choosing the noise amplitude proportional to this regularization. And so what you see is that after some transient regime, so this is a log-log plot. So this transient regime is actually the exponential growth of the instability, I mean, the usual linear instability growth. And after this regime, basically all the curves are saturating to universal low, which is growing as a power 1 of time. And with a constant, you see that is independent of the protocol that you have used to reach this limit. So from this, what we expect is that when we make viscosity to 0, basically this curve will extend up to the smallest time scales. And so that from the very beginning, we will observe a spontaneous explosive separation between different trajectories, between different solutions, and following this universal law. So what does it mean? It means that certainly in the inviscid problem, there is some kind of discontinuity with respect to the initial condition. It means that if you move a bit the initial condition by putting this perturbation, then you arrive to a completely different solution at later time. It's like if you had a shock in the way the solution is depending on the initial condition. And the second thing is that certainly, I mean, now in almost all settings that we can think about, so Nigel was talking about molecular noise. So basically, there is some noise in your environment, which is even very small. So this noise might lead to a very stochastic nature of the equations we are looking at. Okay, so assume that so basically we have this exponential growth of the difference, so which means that one realization of temperature will give one curve, one solution, and another one will give another solution, which means that spontaneously one will observe some stochasticity in our system. So this is the other breakdown, which is the spontaneous breakdown of the Eulerian flow. So now, if I just summarize these things, so the idea is to try to understand if one could provide a unified vision of these things. So I told you, so there are three main things which are broken in the inviscid limit. So the first one is the time reversibility due to the dissipative anomaly. The second one is scale invariance through intermittency. And the last one is breakdown of flows themselves, so both at the Eulerian or Lagrangian level. And the idea is to understand whether the 3D Navier-Stokes, I mean, it's a long-term idea. We'll not be able to answer anything now. But the one idea could be to try to understand if there is some connection between these three broken stability, and if this is enough, or if this is the right framework to select what's happening in the inviscid limit. So one thing, for instance, between the dissipative anomaly and the Lagrangian spontaneous stochasticity, a link could be through this non-uniqueness of the weak dissipative solution. If you provide, if you require to have dissipative inviscid solution, maybe this will mean that you're breaking down the Eulerian flow or the Lagrangian flow by default. Another link, for instance, between dissipative anomaly and intermittency is through the singularities and how they are distributed. This is all the essence of the multifractal approach to understand intermittency. And between intermittency and Eulerian and Lagrangian spontaneous stochasticity, the thing is that maybe this intrinsic randomness, which is due to Eulerian spontaneous stochasticity, could lead to some kind of universal statistics in the way things are amplified by the inviscid equations. So now there are some model flows for which we can partly answer these questions. So the first one is Burger's turbulence. Again, I have these things. So now I'm considering one-dimensional solutions to the stochastic Burger's equation with a stochastic force, which is a white noise in time and large scale, let's say. And now what we know is that if we look at the limit where the viscosity is going to 0, I mean, we have this dissipative anomaly, and everything is understood in the sense that requiring that the solution are dissipating energy is enough to select the right weak solution in the unique weak solution. But in Burger's equation, what we know is that there is no spontaneous stochasticity. Basically, the thing is that maybe, so there are some hints saying that maybe the backward Lagrangian flow would be thought about spontaneously stochastic, but what is clear is that solutions to the Burger's equations are not chaotic. So in the sense that they cannot provide these explosive things. And of course, so now dissipative anomaly is related to some specific singularities which are forming in Burger's equation, which are the shocks, and we know exactly how the shocks are giving intermittency in Burger's equation. So there is another model which is a bit more complicated, which is the Kraken passive scalar, for which again we can think about the same kind of questions. And now, so what we are doing is that we are considering solutions to the advection diffusion equation, so written this way. So the unknown is theta, and the velocity field is prescribed, random, Gaussian, with a given correlation, which is again white in time, but with some prescribed scale invariance in space. Okay? And now we can tune this scale invariance parameter in order to reach situations where the velocity field is not differentiable. So now again, we know that we have a dissipative anomaly, and because of this dissipative anomaly, we know that it requires to have some kind of collapse in the Lagrangian dynamics. So you need to have Lagrangian trajectories which are coming arbitrarily close in a finite time in order to dissipate the scalar energy. And so basically, this means that dissipative anomaly and Lagrangian spontaneous stochasticity are clearly related one to the other. The other thing is that, again, dissipative anomaly is and because of this collapse of trajectories, implies that you are creating fronts in the scalar field. So lines, I mean, manifolds along which the scalar is varying very, very fast. And basically, the thing is, because of this kind of singular structures that you're creating, this is explaining the intermittency, at least heuristically. And now there is another bridge, which is between Lagrangian spontaneous stochasticity and intermittency, which is through what are called the zero modes or the statistical conservation law, which are things which are statistical quantities which are preserved in average, okay, by this spontaneously stochastic Lagrangian flow, and which are prescribing some given scaling depending on how many points you're considering together. And this is how things are, how people are constructing the anomalous scaling laws for the passive scalar. Okay, so there is one missing point in this Kraken passive scalar model, which is Eulerian spontaneous stochasticity. So actually, if you look at solutions to this advection diffusion equation, even if U is very rough, one can construct a unique theta field. Yeah, and this is basically in the framework of the so-called Di Perna-Lyons vision of transport problem. And basically, even if U is just is having, even if U is having this non-Lipschitz behavior, even if the Lagrangian flow is non-unique, ill-defined, still the Eulerian theta can be unique. So now, what I will introduce now, so now I'm coming to SQG. So now, in order to complicate a bit this Kraken situation, so now we have decided to look at solutions to an active scalar transport problem. So we are considering some field theta, which is transported by a velocity field, as it was before, except that this time, the velocity field is itself related to theta through something like this. So basically, the velocity field is incompressible. So now we are considering 2D, 2 dimensions. So it's just the paired gradient of some stream function. And the stream function and the scalar field are related by some operator, which is the power 1/2 of Laplacian, of a minus Laplacian. So what it means, so it's easy to understand it in Fourier space. In Fourier space, it means that the Fourier transform of the velocity field is given by some multiplication times the Fourier transform of the scalar field. And this multiplication, so this is the perp grad, okay? It's just in order to make the thing incompressible. And now you just divide by k. So if we were looking at Biot-Savart, for instance, for the relation between U and theta, here we will get k squared. What does it mean just to have k? It means that U and theta have the same dimension. So theta is also meter per second. And so why are you considering this problem? So first, it has applications because it corresponds to the transport of temperature in a strongly stratified and rotating environment. So it has that, whence the geostrophic, quasi-geostrophic thing. And then, so somehow you can think of it as an analogous to 2D Navier-Stokes. But this time you think about the temperature as vorticity. But now you have to modify the relationship between the stream function and vorticity to this Poisson equation. So as in 2D Navier-Stokes, I mean, there are two conserved quantities. Something which is the Hamiltonian, which is nothing but the integral of theta times psi. And the other one, which is the kinetic energy, which is the integral of theta squared, which is equal to the integral of U squared because of this simple relation. So this equation is developing a turbulent regime at a very large Reynolds number or small viscosities, where there is an inverse cascade of this Hamiltonian, which is the same as the kinetic energy in Navier-Stokes 2D, and a direct cascade of kinetic energy, the kinetic energy being the analogous to entropy. So there are now, why studying these things is because there are analogies with the 3D Navier-Stokes. So the first analogy is that there expect to be some dissipative anomaly, in the sense that if you take the rate of dissipation of the active scalar, I mean, this rate of dissipation, which is nothing but that, is going to a constant when you make viscosity to 0. And now, because of that, there is some equivalent of the Onsagar Criterion, which is now on the increment of the scalar field. The increment of the scalar field should go like a power h with h less than 1/3. So it was not proven yet. So only in one way. So only in the way when you take h bigger than 1/3, then you have no dissipation. But the reverse was not proved. So now, because of that, what you expect is some Kolmogorov scaling. So all the K41 approach is valid, and in particular, the spectrum is expected to be like k to the minus 5/3. But numerics are suggesting, as in Navier-Stokes 3D, some intermittency. Now, other analogies concern the finite time blow-up in the limit of in the vanishing viscosity case, which is still unsettled, and this is how this quasi-geostrophic equation came into the game of mathematicians. So basically, It was mainly by Konstantin, Maida, and Tabak in 1994 that they started to look at the blow-up, finite time blow-up for this problem. And then there are some other things. So like the global existence of weak solution is known, but there are troubles to apply the usual convex integration techniques in order to show that solutions are non-unique. People are not able to show that solutions are non-unique. This is something which remains open. Then, because of this scaling, of course, there is an explosive separation of tracers. So this Lagrangian spontaneous stochasticity could be true. And there is what is called this inverse cascade of errors in the language of geophysicists, which means that there is some kind of Eulerian spontaneous stochasticity. So now what we are considering is the following case. So we are starting from initial data, which is analytic. We start from few modes. Of course, a lot of symmetries, but why considering this? Because this was the historical case considered by Konstantin, Maida, and Tabak. And now, basically, so the initial conditions look like that. And now if it started to develop, so this was the quasi-singular things which was considered by Tabak, but we let things evolve later. And of course, now we have viscosity, so we can go further. And what you see is that after some time, basically, you're developing a turbulent regime where you see that you have many scales which are activated. And in this turbulent regime, so of course, we have very strong large-scale anisotropies, which are due to our initial data. But what you see when you look at the spectra at different times, what you see is that so you start developing an inertial range, and after some time, you get a turbulent solution with a clear k to the minus 5 approximately k to the minus 5 low regime, inertial range. So now with this solution, so basically we have, our idea was to try to vary the viscosity, to look at the limit of vanishing viscosity of this solution. And so this is an evidence of a dissipative anomaly in this case. So this is the dissipation rate of kinetic energy as a function of time for decreasing values of the viscosity. And what you see is that after some time, which is some time after which the solution is going in this turbulent regime, all the curves seems to collapse on the top of each other, which means that dissipation rate is becoming independent of viscosity. And now if you look at the same thing, but this time for the other conserved quantity, the Hamiltonian, so now what you see is that you have a clear dependence on viscosity, which means that there is no, I mean, that the Hamiltonian is not affected by this dissipative anomaly. So the other conserved quantity, and the rate is very small, and this other conserved quantity is staying almost constant during the time of our study. So in order to make a hand-waving understanding of this turbulent regime, basically what you can think is that actually the fact that one is getting this turbulent regime is more or less independent of a finite time blow-up. In the case where we take the blow-up, of course, at zero viscosity. And then we have different scenarios. So either there is a finite time blow-up, which means that at time t star, the solution is becoming singular, that you're activating arbitrary small scales. And in that case, it will mean that this turbulent time, after which you're turbulent, is just, you just need to pick something after this singularity time. And then it's becoming independent of viscosity. There's just this t star, which is telling you what is the time after which you get some dissipation, even if you have no viscosity. So now there is another thing which is something which is believed for this equation, which is this double exponential growth of gradients, which means that gradients of theta are growing like a double exponential, super fast. And in that case, this turbulent time will go like a double log of the viscosity. Okay, because you just require to reach your dissipative scale somehow through this double exponential growth of gradients. And then in numerics, I mean, if you try to look at a double log of viscosity, you will never see anything as a function of viscosity, except if we had an infinite computer. So which means that we don't mind. I mean, we don't care. We don't care if it's log-log or if it's something related to blob. So now we are going to look what's happening in this turbulence regime. So the first thing is that there is intermittency. So now here what is shown is the flatness of the kurtosis, if you want, of the velocity gradient, which is the fourth order moment divided by the square of the second order moment, the gradient of theta. Again, as a function of time, so this is dimensionless, okay? And what you see is that as a function of time, for different viscosities, basically it's increasing when you decrease viscosity. Okay, so which means that flatness depends on the Reynolds number. And this is a sign of intermittency. And now the other thing that one can measure is measure the distribution of the coarse grain dissipation rate of the theta field. And again, what you see here, that so now it's a fixed value of viscosity, different scales. And what you see is that there is this multifractal-like distribution, where all the distributions are collapsing as if the dissipation was scaling like L to the alpha on a fractal set with a dimension d of alpha. And this is this d of alpha, measured from our simulation. So with these two things together, we can predict how to rescale this behavior in order to have a collapse, because from multifractal arguments and knowing these curves, we can predict how the flatness will grow like as a function of Reynolds number. And this is what is shown here, is that now we use this data to get some exponent for the flatness, and we rescale the flatness by this exponent, and we show it again as a function of time, and it seems to collapse, reasonably collapse. So now, what about the Lagrangian flow? So there is, in this specific case of an active scalar, or of any scalar, even if it's spacive, there is a very strong relationship, as in the Kraken model, between kinetic energy, I mean, energy dissipation of the variance of theta and the spontaneous stochastic behavior of Lagrangian trajectories. So this you can see it through the Feynman-Kac formulation of the scalar field theta. So now you assume that theta, so theta can be written as the mean of initial value of theta at an initial position of a given equation, which is this one, so which is the equation for tracers that I'm perturbing with some noise with amplitude viscosity. This is just, if you assume that and that, then through Feynman-Kac you can show that theta is a solution to the SQG equation. So except that, of course, in this average, the U field depends itself on theta. So I mean, it's a bit, I mean, I've simplified a bit the picture, but it remains true. And so now what it means that if you want to know the solution at time t at a given position x here, basically you have to take this equation backward, look at all the realization of your diffusion. So you go backward in time up to the initial time.
Jeremie, sorry for interrupting.
Yes.
Your 40 minutes are up, but please continue. No.
Okay. Yes.
No, continue. It's okay. I mean.
And basically, what you get is that the solution at time t is given by averaging the initial value of theta over all these possible trajectories. And now, if you compute the dissipation, so there is a kind of fluctuation-dissipation relation, which is telling you that the change in energy of the global solution is equal to the variance of this theta that you're transporting. Okay, so it's relating dissipation to fluctuations of this Lagrangian trajectory. So now the thing is that in order to get a dissipative anomaly, so in order to have this non-zero, you need this variance to remain non-zero in the limit of vanishing viscosity, which means that your distribution has to remain a probability distribution even if you forget about the nodes. So now this we could try to understand it numerically a bit better. So here what is shown is the dissipation field at a given time, the corresponding forward separation. So as a function of the initial position, how far two particles will be in the future. Same backward. And what you see, so that the three fields are clearly correlated. And now, so of course, the dissipative anomaly is just telling you correlation between these two things. But because we are incompressible, it also means that there is also a breakdown of the forward flow. So this is now the mean square separation as a function of time, backward, forward. So you approximately see a T-cube law, and you have to believe in it a bit. And these are for different, so decreasing viscosities. This T-cube is going further and further to the left, both backward and forward. So now no, it's 40 minutes. So now so basically there is something which is a difference with Navier-Stokes, which is the fact that in the SQJ system, the relative dispersion is actually keeping a very strong dependence on the initial data. So you remember that I was showing you that in Navier-Stokes 3D, you take different initial separation, they all collapse to the same curve. So now it's the same kind of plot, R square, different initial separation as a function of time. So what you see is that there is up to the very large time where the separation is starting to diffuse, there is a very strong dependence on the initial separation. So what we think is that either we are in the same non-universality class as in the weakly compressible Kraken model, for which, so we know in the weakly compressible Kraken model is that there is a very strong memory of how long you are spending at zero separation, which is persisting in the limit of zero diffusivity, and this is affecting the statistics, or it's because since we are considering a deterministic flow, the decaying problem, a finite size and a finite viscosity, maybe this could be just numerical artifacts. So now concerning Eulerian spontaneous stochasticity, so now what we are doing is that we are perturbing at some time where we are in the developed turbulent regime. We are perturbing with some amplitude epsilon. And so this is the base solution, so in a quarter of our domain. And now if it's perturbed, you see that at large scale it doesn't change much. So we perturb it with some energy. So epsilon is the energy of the spatial noise that we are adding. So we are decreasing this perturbation. I'm sorry, I should have inverted this. No, I think that this one, no, I think I did a mistake on this. This one is 10⁻⁶ and 10⁻⁴. And so what you see is that at large scales, of course, we don't change much at that time, but at small scales, I mean, we have very different. So these are zooms of the squares. We have different profiles of the scalar field. So now, if we try to measure the separation energy, as in the case of Kelvin Amos, as a function of time, and for different values of epsilon. So basically, what we do see is that the separation energy is again going through first an exponential separation, as expected, and then to something which is more explosive, but this time which depends on the amplitude of the perturbation, as for the Lagrangian separation of trajectories. So I will not talk about the spectrum. So now, so basically, again, we observe that the dependence upon the perturbation size is persisting at large times. And again, we don't know if this could be an effect of deterministic decaying settings, finite size, and finite viscosity. Still, so just to summarize, so basically what I've shown you is that the deterministic SQJ flow are becoming turbulent when the viscosity is going to zero. That they are sharing distinctive signatures with Navier-Stokes turbulence, so irreversibility, intermittency, and possibly spontaneous stochasticity. But that the spontaneous stochasticity of SQJ flow is a bit different from what we observe in Euler. So it could be a kind of tempered spontaneous stochasticity, so which means that the dependence on initial condition could be neither differentiable, as it is in chaotic system, nor discontinuous, as it has been observed in Euler, for instance, but something in between with a singular dependence on the initial perturbation. So imagine that this means that the growth is proportional to epsilon. This is growth proportional to epsilon to the power 0. And this could be epsilon to some power in between 0 and 1. And so then, so what we are now working on is to try to find other instances of such a behavior, simply in even more simplified model. And then we are addressing the question whether the 2D Navier-Stokes is also in the same class, if it has this tempered spontaneous stochasticity. And on for the rest of the PhD of Nicolas, there is also another point that we are going to study, which is the case of force dissipated solutions in a statistical steady state, and to understand if the presence of an inverse cascade of the Hamiltonian is showing something to this picture. Okay, thank you. Sorry for the delay. Jeremie had the question.
You have a question?
Jeremie, for the velocity gradients you mentioned, so does it obey exactly the same sort of Nelkin-like relation? The velocity gradients growing with Reynolds number, the exponents?
So the velocity gradients are more singular than the theta field. We didn't look at the gradients, the velocity, but it's more singular. And in particular, it can be infinite. So at discontinuities, if you have a concentration of the theta field on a line, then you have immediately close to this line, you have infinite values of the velocity field. So certainly the gradients will be even more intermittent. This is my guess, but we have not looked at it. Good suggestion.
Yes.
Yeah. I think dissipation is normally considered as viscous dissipation in any turbulent flow. And unfortunately, I mean, there's another way of dissipation. Dissipation could happen due to acoustic energy also, dissipation.
Yeah, of course,
so
in
I
real
don't know,
situations,
you mentioned shock and all those things. So, I mean, so if you consider that, even in inviscid flow, there could be dissipation, and I don't know whether you are considering that type of dissipation.
So I'm considering solutions. I mean, the context I'm looking at are solutions to Navier-Stokes, incompressible Navier-Stokes. So,
Yeah.
So of course, if you want to compare these things to experiments, you might have limits by due to acoustic waves or weak compressibility somewhere, etc. But the thing is that at the moment I'm just trying to build an understanding of the solutions to Navier-Stokes.
Yeah, so that means to say, if you compare even inviscid flow, unfortunately, I mean, experiments cannot be done, real experiments. So, and measuring those dissipation due to, I mean, pressure waves or shock wave diffusion, or, I mean, shocks, acoustic diffusion, that is difficult to measure. So you cannot compare all these things to any experiment.
The idea of this approach is also to provide some prediction on how things are depending on Reynolds number.
Oh, okay.
Yeah. Can I ask one quick? You have a question, Uriel? Wait. You need a microphone.
Yes, much better. Yeah. It is. I mean, I was strongly convinced by the very nice figures you presented to us. And of course, there are certain things that are almost unavoidable based on those, but there are also cases where even the best figures are a bit fuzzy. The question is, can you find special cases, maybe in 2 dimensions or so, where you can derive a rigorous result that can rule out some of the things?
So the relationship between energy dissipation and Lagrangian spontaneous stochasticity, I mean, this is a rigorous result. So maybe rigorous result in simplified models like shell model like. This could be possible also. But then for the full SQG, at the moment, I'm not sure that I will be able to provide easily a theory.
Ask one last question. You skirted the issue of the possible finite time singularity. Given the resolution you have, are your data consistent with the finite time singularity or not?
No, so basically what we do observe, so I can quickly show you that. So basically the idea, so now if there is a singularity, it will occur somewhere at you see the growth of the gradients here from the initial time. So it will occur somewhere at around time 10. And what we do observe in this quick growth is a double exponential.
I see.
As it was observed in the group of Okitani. So basically so we are not able to see anything else. And we have this double exponential, and then viscosity is
what sort of resolutions did you go to in your?
We went up to 8,000 square.
8,000 square. Okay, fine. Thank you very much. Perhaps we should have a break now. And since we are running a bit behind schedule, we'll start at 11. And then again, we'll see how the sessions go because they're 40-minute talks. Okay, thank you very much.